Hello everyone, welcome back. This is part 5 for the chemical bonding series. In this video, we're going to talk about three topics in the chemical bonding. The first one is the coordinate covalent bonding. The second one is the resonance structure and the exceptions to the octet rule in covalent compounds. In our previous video, we've talked about covalent bonding, the definition, formation, and representation of covalent bonding. So we have seen that covalent bonds can be single, double, and triple, depending on the number of pair of electrons that are shared between the atoms. If you haven't watched our previous video yet, feel free to go back and watch it. Let's begin with coordinate covalent bonds or dative bonds. What are coordinate covalent bonds? These are special types of covalent bonds in which one atom provides both the electrons for the bond. These are called coordinate covalent bonds. Let's look at ammonium ion or the NH4+. So this is the structure of ammonium ion. As you can see, this is labeled differently. We will see why. So we have ammonia. You can remember from our previous video, the Lewis structure of ammonia is like this. We have lone pairs of electrons around ammonia. And when a hydrogen ion, which is just a proton, comes along the ammonia, when a hydrogen ion, which is just a proton, comes along ammonia, nitrogen from the ammonia will donate both of its electrons to hydrogen, forming a new bond, which is called coordinate covalent bond. And just like that, we make coordinate covalent bonds. Another example for coordinate covalent bond is carbon monoxide or CO. So the Lewis structure for carbon monoxide is CO, and then there is a new bond. This is the Lewis structure of CO. As you can see, one of these bonds is an arrow pointing from oxygen towards carbon. This shows that for the two electrons here for this bond are both provided by oxygen. This is another example of coordinate covalent bond. Another example is hydronium ion. Hydronium ion, or this is when hydrogen ion is added to water molecule. Let's look at it. So we have water first. This is the Lewis structure of water. We have two lone pairs of electrons around oxygen, and then when a hydrogen ion comes across this water molecule, this lone pair of electrons from oxygen will come and attack this hydrogen, forming a new bond, which we call coordinate covalent bond. Now this is our new bond. This is our new bond, okay? But earlier I said that hydrogen ion is just a proton. What does that mean? How is hydrogen ion just a proton? So originally hydrogen has one electron and one proton. So when it becomes hydrogen ion, a positive ion, meaning it has lost one electron, basically the only electron it had. So we're only going to be left with just a proton. That is why I'm saying hydrogen ion as a proton. So this is another example of coordinate covalent bonds. Now let's talk about the resonance structures. So what are resonance structures? So a covalent compound cannot be represented by just one Lewis structure. Instead, it can have multiple or many valid Lewis structures. So the actual structure of the molecule will be the hybrid of these resonance structures. Let's look at an example. The first example will be the ozone molecule. In ozone molecule, we have 3 oxygen atoms. Let's draw the Lewis structure of ozones. So we have 3 oxygen atoms. This is one possible Lewis structure. We can check. This oxygen has 8 electrons. This oxygen has 8 electrons. This oxygen has again 8 electrons. This is one possible Lewis structure. But this is not always the case, because this multiple bond, this high electron density, can move to this bond or to the other oxygen-oxygen bond, forming another resonance structure looking like this. The double bond now will be here, and this will be the single bond. 1, 2. This is another valid Lewis structure for ozone molecule. But actually, the actual structure of ozone molecule lies somewhere between these two structures. Okay, this is the actual structure is the hybrid of these two structures, which will look like. So the actual structure of ozone looks like something like this. So as you can see, we have represented this double bond. So we don't know where the double bond will be at a time. So we represent it by dashed lines. Okay, this is the resonance hybrid structure of ozone. What do we call this? These are called resonance structures. So this one is resonance structure 1. This one is resonance structure 2, and this one is called resonance hybrid. So this is the actual Lewis structure for ozone molecule. So what are resonance structures again? So we know that some molecules, some covalent compounds cannot be represented by just one Lewis structure. They might have multiple or many valid Lewis structures. So to represent that, we use the resonance structures, but the actual structure for the molecule will be the resonance hybrid. Another example is the nitrate ion or the NO3 minus ion. Now let's look at the different possible or plausible Lewis structures for nitrate ion, and then we will see the hybrid resonance structure. This is the first possible Lewis structure for the nitrate ion. Of course, we're not gonna forget the negative ion here. So this is the first possible structure or the first resonance structure for the nitrate ion. Okay, this can also be written as we can have the double bond in this. So let's write it again. Now this is the second plausible Lewis structure for the nitrate ion. Of course, we have our negative charge. Of course, we have our negative charge. And then the double bond can also be formed with this oxygen. So let's look at the another structure as well. So this is also the same as. So this is the third resonance structure for nitrate ion. Okay, so this is structure 1, resonance structure 1. This is resonance structure 2, and this one is resonance structure 3. But the actual structure or the actual Lewis structure for nitrate ion does not look like one of these. Instead, it's somewhere in between these three, which is represented by the resonance hybrid structure. So this is the resonance hybrid structure, which is not this, or this, but we don't know where the double bond will be at a time, so we represent it using dashed lines. This is the resonance structure of the nitrate ion. So this is resonance structure 1, resonance structure 2, and this is resonance structure 3, and then this is the resonance hybrid structure. So resonance structures is not just theoretical. It's very crucial to understand the molecular stability. Example here is benzene. So benzene has a unique property, which is the aromaticity, and this is all due to the fact that it has resonance structures. Okay, so benzene C6H6 can be represented by this. This is resonance structure 1, but as you can see, this double bond or this electron density can move to this, and then this one will shift to this, and then this one will shift to this, and then we'll come to this structure. So as soon as this structure is formed again, this double bond will be shifted again. So this structure will be will again get back this structure. So the actual structure of benzene, this is the second structure. So the actual structure of benzene would look something like this. Okay, we represent it using dashed lines because we don't know where the double bonds will be at a time. So this is the resonance hybrid structure. Resonance hybrid structure of benzene. Now let's talk about the exceptions to the octet rule. While the octet rule works for many compounds, there are three major exceptions. Being the first one is incomplete octets, those that have below octet, meaning less than 8 electrons around the central atom, and then expanded octets, those that have more than 8 electrons around the central atom, and the odd electron species. These are the three exceptions to the octet rule. Let's look at an example. The first example will be BF3. So in boron trifluoride, let's draw the new structure of BF3. We have boron in the center and 3 fluorine atoms surrounding it. So this is boron trifluoride. So as you can see from the new structure of boron trifluoride, boron has 6 electrons in its surrounding. As you can see, boron in BF3 or boron trifluoride has 6 electrons around it, but it will still be stable because it's okay to have less than 8 electrons for some elements, mainly group 2, and group 13 elements. So group 2 and group 13 elements can have electrons less than 8 in their surrounding and then be stable, okay? This is an exception. So boron trifluoride has an incomplete octet. So most of the time, boron, beryllium, these metals or these elements in their compounds, most of the time they have below octets or the incomplete octets. Now let's talk about expanded octets. Elements in period 3 like sulfur, elements in period 3 and beyond like sulfur, they can have more than 8 electrons in their last shell. For example, let's look at sulfur hexafluoride. This is second example, SF6. So let's draw the new structure of sulfur hexafluoride first. So we have sulfur in the center and we're going to have 6 fluorines around it, okay? So this is the new structure of sulfur hexafluoride. We have sulfur having 2, 4, 6, 8, 10 and 12 electrons. Sulfur now has 12 electrons around it, which is obviously more than 8. So what do you think is the reason behind this? Because elements in period 3, including sulfur, in period 3 and beyond, including sulfur, they can use their d orbital in bonding. This is why they can have an extended octet. But elements in period 2 can only have 2 shells, and then in the first 2 shells, they don't have any d orbitals. But when it comes to the third period elements, they can access their s, p, and d orbitals to make bonding. That is why they can have extended octet. And sulfur in sulfur hexafluoride is an example here. So the second exception is expanded octets. So when they have 8 electrons around the central atom, we call it an expanded octet. Lastly, we have odd electron species. An example here is nitrogen monoxide or the nitric oxide, which is represented by NO. Now let's draw the new structure of nitrogen monoxide together. So valence electrons in nitrogen are 5, plus valence electrons in oxygen are 6. 5 plus 6 is 11 electrons. So totally we have 11 electrons. So is this odd or even number? No. So 11 is odd. So we have 5 pairs of electrons and 1 single electron unpaired. So nitrogen monoxide or nitric oxide is obviously an exception to the octet rule. Let's check. So let's draw nitrogen and oxygen separately. How many valence electrons do we have in nitrogen? We have 5. We have 5, and in oxygen we have 6. So now let's make bonds and let's try to make them stable. So they will make a double bond. Now as you can see, oxygen is stable, but nitrogen has 1, 2, 3, 4, 5, 6, and 7. So nitrogen has odd number of electrons. So such substances or odd electron species are also exceptions to the octet rule. So in today's video, which is part 5, we have so far discussed about the coordinate covalent bonds or dative bonds. These are types of bonds, types of special type of covalent bonds where both the electrons for the bonds will be provided by one of the atoms, okay? And resonance structures are multiple possible loose structures for a given covalent compound. And then the exceptions to the octet, we have three exceptions. The first one being below octet or incomplete octet, the second one being expanded octet, and the third one being odd electron species. So this is it for part 5. In part 6, we will we'll go over the VSEPR theory. This is an acronym which stands for valence share electron repulsion theory and the molecular geometry. So thank you for watching, thank you for subscribing and liking the video. Feel free to comment whatever questions you have. Thank you again. See you in the next video.